we can algebraically solve for the change if we can set it up in the right fashion. Even if we can't numerically solve directly, we may be able to approximate and estimate and use those values to numerically get to our answer computationally. Just having that equilibrium expression is enough. But there are other ways. Sometimes we look for simplifications. The quadratic formula is the long way, and it can always be done, but it's not the most efficient way. So let's take a look at one way to simplify. So here's an example. I've written it out. It's pretty much the identical reaction of ours. And so we can build our ice table, our initial concentrations, and our zero concentration for our iodine, and our zeroth concentration for our HI, our change minus x, plus 2x, and that leaves equilibrium values of 0.240 minus x and 0.240 minus x and plus 2x as our equilibrium values. We can then plug this into our equilibrium statement. The whole purpose of getting these equilibrium values is to arrange them into the equilibrium statement, which is HI squared divided by H2 and I2, and we can plug them in and get a form that looks like this: 2x squared divided by 0.240 minus x, 0.240 minus x equals 54.3 for this particular problem. So now we have everything we need to solve for the quadratic. We can take this material, FOIL this out, expand this polynomial, and then multiply and solve and rearrange. But it's not the most efficient, because in this particular one, these two values are the same, and so we can rewrite this into 2x squared 0.240 minus x squared equals 54.3. And because we can write these two together, we see that this is a perfect square. This is 2 square units, and so if we took the square root of both sides, we would eliminate this square term. And so this becomes 2x over 0.240 minus x is equal to square root of 54.3. So once we have it in this form, we have to rearrange. This becomes 2x is equal to this number, 7.37 times 0.240 minus x. And then we can multiply this out, and it becomes 7.37 times 0.240. This becomes equal to 1.768 minus 7.37x. 2x is equal to 7.37 minus x. So, combine these terms to produce this equation, and then set it equal to 2x, and now we can solve for x. 1.768 is equal to 9x, 9.37x. Therefore, x will be equal to this 1.768 divided by 9.37. .188 will be equal to our x. Now, that It's not the problem, that's not the answer, that's the step to the answer, and so we use that to plug in the rest of these values. And so this becomes, so we have now have our target values, and remember, to check them, we plug them back into our equilibrium constant. So HI, concentration, 0.3776 molar squared divided by 0.0512 molar times 0.0512 molar will equal, you do the math, and you get 54.9. .4, which is in good agreement with our answer. Right? So our correct answer, dropping our sig figs down to the 3 that we started with, 0.378 molar HI and 0.0512 molar I2 and H2. All right. So you do not need to go through the quadratic every time. Ideally, with a perfect square, it should simplify. There's another simplification we can use too, and that is related to the equilibrium constant.